is called the Milky Way. And it's what I study. It's the galaxy that we all live in. And it's made of about 100 to 200 billion or so stars. So stars like the sun. So the sun is a star. And there's 100 to 200 billions of stars out there in our galaxy alone. And so for me, I'm most interested in things like, well, how the heck did you form like a galaxy like this? How do you form a galaxy? How do you evolve it? And how is it structured, right? It's not just a blob of stars that you might see in a child's book. The stars are kind of oriented beautifully along this Milky Band. So how do we get that? And so as a galactic archaeologist, this is what I get to do every day, and something that I absolutely love and adore. It's the ability to be able to study the Milky Way, and particularly what I'm interested in is studying the chemical composition or chemically tagging stars across the Milky Way. And so when I'm at cocktail parties or things like Astronomy on Tap, I'll often say that I'm nothing more than the Indiana Jones of the Milky Way. So the Astronomy on Tap here in Austin, my nickname in the Astronomy on Tap is actually the Indiana Jones of the galaxy, because kind of like Indiana Jones would go out and search for human artifacts and try to figure out how some ancient civilization came about. I do the same thing, but I just do it with stars. And every star in the night sky is essentially a fossil. And that's for two reasons. Firstly, distances in space are very vast. And so that means that when I look up at a star that's on the other side of the galaxy, I'm not seeing as that star is now, I'm seeing as it was maybe tens or hundreds of thousands of years ago. The same is true about the sun, actually. So if you look up at the sun, which you should not do without protective lenses, you actually are not seeing the sun as it is now. You're seeing the sun as it was about 8 minutes ago, because it takes 8 minutes for the light from the sun's surface to traverse space and get to our eyes here on Earth. And the second reason why every star is a fossil is because the chemical composition, the chemical DNA, if you will, of a star generally doesn't change over the course of its life. And so you can look up at a star, and if you study its chemistry, then you see what the universe is doing chemically, however many years ago that star formed. And so it's similar to human beings, right? I can take a DNA out of a child or from an older person and figure out, for example, how human beings might be evolving. And we can do the same kind of things with stars. And so these stars form the basis of a galaxy. I haven't really told you what a galaxy is. I probably should. A galaxy is nothing more than a collection of stars and dust and gas and humans and cats and dogs and everything that you know and love, and it's held together by mutual gravity. This is the first kind of image, if you will, of our galaxy, the Milky Way, from William and Caroline Herschel, who are pictured here. And they basically mapped stars for the first time and found that the galaxy looked like this little tentacle-like blob. And it was also believed at that time that the sun was at the center of everything, because the Earth was at the center of everything, because humans were at the center of everything. We now know that that's not entirely true, and that's thanks to galactic observational astronomy, and that's actually what I get to do. So I'm a galactic observational astronomer. I go to telescopes around the world. This is me at various telescopes from Hawaii all the way to the Canary Islands and in Spain, to California, to Arizona. So I get to travel and go up various mountains and look at the stars. So it's one of the reasons why I absolutely love the job that I have. And in doing this, galactic observational astronomers found that our galaxy is not, this amorphous blob, and we're not sitting at the center. In fact, our galaxy probably looks like this. This is an artist's impression of our galaxy. I should mention that it's not a real observation of our galaxy, and that's because we haven't been able to get outside of our galaxy. We actually haven't traveled past the moon to be able to take a picture of the galaxy. So we have really no idea what the galaxy looks like from a top-down perspective, and we probably won't know for millennia. But this is the best impression that we have of what we think the galaxy looks like. And so you can see that it's a beautiful spiral galaxy. There's wonderful spiral arms. And there's a bar in the center. So the spiral arms are coming off this bar. And so our galaxy is called a barred spiral galaxy. And the sun is not at the center of the galaxy. It's about 2/3 of the way out, kind of on the outskirts, if you will. And it is about 28,000 light years away from the center, On an orbit, it's about 230 million years. So the last time the sun was in the current location was right around the time that human beings began to evolve, actually. And so the way I like to tell this to people in Austin is if downtown Austin is kind of like, in the center of everything, this would kind of, the sun would probably be somewhere near like Round Rock, Pflugerville, that kind of area. San Antonio, I'm a little bit less familiar with, but if I'm guessing if the downtown area was San Antonio, then here would probably be something like San Marcos. Would probably be the closest geographic analogy for those of you who are joining us from San Antonio, from Texas, from Austin. And our galaxy has 5 different components in it. It's got a thin disk, a thick disk, a halo, and a bulge. And this is the kind of a cartoon image of our galaxy. And the way I usually like to describe it is in terms of breakfast food. So because I absolutely like food and I actually like breakfast. So like the galaxy is kind of structured in such a way where the thin disk of the galaxy, which is this component here, this really thin component, is kind of like a French crepe. It's very thin. It's extremely thin. And then surrounding that French crepe, imagine you have a fat American pancake. So you have your French crepe, and you've got it surrounded by a fat American pancake. That is the thick disk. And then if you want to figure out the flow, then what you do is you take that crepe that's surrounded by the fat American pancake, and you batter it up and you deep fry it. And the deep fried batter on the outside, that's the stellar halo. And then finally, in a very unhealthy fashion, you put butter, you put a glob of butter in the middle, a stick of butter, and that is the bulge. So that is our galaxy. That's how it's structured from a very breakfast-like analogy. And the way we know it's structured this way is by not only looking at how the stars are distributed across the sky and the galaxy, but also how they look, how they're moving, and also how they appear chemically. And the way we do this, especially from the chemistry perspective, since this is what I do, and I'll skip everything else and just talk about the chemical side of things, is through something called spectroscopy. And so this is a really good example of spectroscopy is actually this image up here, which for those of you that are a little older in the crowd might recognize this. This is the Pink Floyd album cover, Dark Side of the Moon. And so if you take white light and you pass it through a prism, you get the beautiful color rainbow, the Roy G. Biv, the red all the way down to the violet. Now, what they don't show you in the Pink Floyd album cover is that if you actually do this in real life and you do this with the sun, you actually get an image like this in the background. This is actually another way of looking at the sun. And so this is our color spectrum from violet down to red. And what they didn't show you was all of these little dark bands. There's like all of these dark bands that appear. And each one of these is actually caused by the absorption of a different element in the atmosphere of the sun. And in fact, the size and shape and structure of these dark bands, like how wide they are, how big they are, how dark they are, allows me to determine exactly how much of each element is in the atmosphere of the sun. So to a trained eye, for example, this beautiful big absorption feature, this beautiful big dark band, this is hydrogen in the atmosphere of the sun. And this line here, that's sodium in the atmosphere of the sun. Oh yeah, and this line here, that's magnesium in the atmosphere of the sun. So I can look at an image like this and actually figure out how much each of the different elements are in the atmosphere. And luckily here at Texas, particularly at UT, we're actually a world leader in doing this type of spectroscopic analysis for the chemical composition or the chemical DNA of stars, because we have McDonald Observatory out in West Texas. Here are 2 telescopes that I actually use out in West Texas. So if you drive about 7 hours west of Austin, you will reach this particular set of telescopes, and I get to use these. And my graduate students get to use these every semester. And armed with spectroscopy, we actually are able to explore not only the galaxy, but also the chemical composition of stars across the galaxy and figure out where they came from. Now, from these methods, we've been able to deduce some really interesting things about the origin of the elements. And one thing is kind of in this beautiful composition figure from a colleague of mine, Anna Frabel. And so at the very beginning of the universe, you got the Big Bang, and that creates everything. It's this massive explosion at the very beginning of the universe that creates everything. But what it actually creates is nothing more than hydrogen, helium, and trace amounts of lithium, and that's it. Now, that's not enough to create life, right? Our blood is largely iron, our bones are carbon, we're breathing oxygen and nitrogen. So where the heck does all of that come from? Well, the answer is it actually comes from stars. So the first generation of stars that form, we call them population 3 stars. They're really big and they fuse hydrogen to helium, helium into carbon, carbon into nitrogen, and they just move their way up the periodic table. And then they explode. And when they explode, they give all of those nucleosynthetic guts, all of those enriched materials to create next generation of stars. And those stars are now enriched. These are supernova explosions. Those stars are enriched with all of this material that can then form a new generation of stars. Those stars live, they die, they explode in these supernova explosions, and they form heavier elements like titanium and magnesium and nitrogen and oxygen and carbon and iron. And more and successive generations of stars do this over and over and over again, and they form heavier and heavier elements. And that's how we get the elements that we see, but that's also how we get the elements that we're all made of. So when Neil deGrasse Tyson says that we're stardust, we actually are stardust. We come from the interiors of stars and that have exploded and given their enriched guts back to the interstellar medium, back to the universe. And so this is the periodic table and showing how each of those elements are formed from hydrogen to helium to trace amounts of lithium, which are formed in the Big Bang. But many of these other elements that are green, they're formed primarily from the explosions, the supernova explosions of these massive stars. Then the even heavier elements, the golds, the nickels, and so forth, well, we think those are actually formed by even more energetic explosions caused by the coalescing and merging of two neutron stars. And I don't really have time to talk about what those are, but I just wanted to show this, showing that the wonderful thing about spectroscopy and the work that we do in galactic astronomy is that we've been able to deduce not only how the galaxy formed, but also how the elements in the periodic table formed. So for the rest of this talk, I do want to make one quick nomenclature or one quick terminology that we use in astronomy. In astronomy, in most areas, right, metal, when we say metal on the periodic table, we usually are thinking about things like down here. We're usually thinking about like zinc or iron, because those are metals. But in astronomy, because hydrogen and helium are just so dominant, everything else on the periodic table, except for hydrogen and helium, are what we call metals. Okay. So now that you know a little bit about the elements and how they formed, how does that, why do I care in regards to the galaxy? Well, this is the most up-to-date picture we have of the Milky Way. This is the best image we have to date. And you can actually see the beautiful galaxy. This is the dust lanes. Each of these dark bands are actually dust in the galaxy. You can see the bulge here in the galactic center, and that's metal rich. It's enriched a lot in all of the elements, except for hydrogen and helium. The thin disk is also very metal rich. The thick disk is much more metal poor, and this halo of stars around it are actually extremely metal poor. And there are actually two small galaxies, dwarf galaxies, that the Milky Way is currently eating up, cannibalizing, called the large and small clouds. And there are some debates about these components, and that's what my group really focuses on. My group actually works on the components of the Milky Way. And this is my group back before COVID, when we were all here at UT at the Shark Tank. And we focused very heavily on trying to understand the Milky Way, but we did this using McDonald Observatory here at Texas, the Texas Advanced Computing Center, another wonderful resource we have at UT, and the Giant Magellan Telescope, which is being built now, that UT is a founding member of. So these are some of the resources that we use. And some of the questions that we wrestle with, I'm just going to throw up 6 questions that we work on, is things like, how did the Milky Way come to be? How does its components form? What are the important physics involved? And how are the elements made? And what can they tell us about the galaxy? And of course, I could spend hours on each one of these questions, but I can't today. So what I will do is spend a very short period of time just talking about the very first one, how did the Milky Way come to be? Because that's the other part of my talk. So it depends on who you ask. If you ask a Greek mythology, they'll say that the Milky Way all started because of this guy. Now, for those of you who are old enough to remember Disney, the cartoon, which I'm sure they're going to turn into a live action because they're turning everything into a live action. I recently saw Cruella in theaters on Friday. Um, Here is the Milky Way, at least in Greek mythology, forms from Hercules. And the story goes that Zeus, who's pictured here, had a child, Hercules, with a mortal woman. And but Zeus was married to Hera. And so Zeus was very fond of Hercules. And so what he did was he came to Earth and he grabbed Hercules and he gave Hercules to his wife Hera to nurse. The idea was that if Hera nursed Hercules, then that would give Hercules these immortal powers. The problem was Zeus gave Hercules to Hera to nurse when she was sleeping, and so she didn't realize that she was nursing this child. So when she woke up, she pushed the child away, out came some breast milk, and that milk became the Milky Way. And in fact, the Milky Way, the word galaxy, which we use today, galaxias, is actually formed from the Greek word galaxias, which is actually derived from the Greek word milk for this exact reason. So that's the Greek mythological story behind the Milky Way. But if you come closer to the United States or to the native lands of America, and you ask somebody who's a Cherokee, they think it actually started because of a dog. So the story for the Cherokee goes that there was an old couple milling corn for the winters. They were basically creating cornmeal and storing it in these bags for the winter. And unfortunately, there was someone coming in and stealing the cornmeal overnight. When they looked at who was stealing the cornmeal, they looked at the prints, and it was this dog print. But it wasn't like a small dog. It was like a massive, massive dog. It's called a spirit dog. And so they decided they needed to scare off this dog in order to keep their cornmeal for the winter. And so what they did was they stayed up one night, they waited until the spirit dog came in and grabbed its fangs into the cornmeal, and they banged pots and pans and they made a lot of commotion, and the dog got scared. And it got so scared, it ran into the sky with the cornmeal, leaving a trail behind called the Milky Way. So that is the Greek mythological, or that's the Cherokee story behind how the Milky Way came to be. Of course, today we don't think that the Milky Way came to be either through Hercules or through a spirit dog, but modern science today thinks that it formed in two different ways. The first is this idea of monolithic collapse, which is that you take a big gas cloud and you just let it collapse because of gravity. And that collapse allows you to form stars, and that creates a galaxy. And then if you want to form a disk galaxy, you just give it a little bit of a spin, a little bit of a kick at the beginning. And kind of like an ice skater, when the ice skater pulls their arms in, same thing as the galaxy collapses, it spins up into a disk. So the similar idea with pizza, a pizza dough, you spin a pizza dough up into a disk. That's what happened in our galaxy. And the second idea is this idea of hierarchical galaxy formation, just a fancy word for saying galaxies eat each other. So this is a modern simulation just showing you at the beginning of time what happens. Again, a computer simulation showing you that each one of these is a star. Each point of light is a star bursting into existence as the galaxy or as the universe evolves. And these small proto-galaxies like this one is about to get eaten, cannibalized by the galaxies, by the big galaxy here at the beginning, in the center part. And so the galaxies grow by cannibalizing and eating each other. And we likely think that happened here in the Milky Way. To figure it out, of course, we actually have to not only figure out the motion of the stars, but we can, each one of these, it's very likely, we think at least, that each one of these stars that were born in one of these galaxies is chemically distinct. And so we can track what the Milky Way has eaten by chemically characterizing all the stars in the galaxy. And so that's something that my group is doing. We're doing all kinds of chemical tracking in the galaxy, trying to figure out how galaxies came to be. And that's something that we're doing in binary star systems. So we're looking at two stars that we think were born together, and we're tracking how their chemical composition are changing over time. In some sense, we're basically looking to see whether stars that were born together are chemically identical or chemically fraternal. And ideally, stars born together, like in all stars born in this galaxy, right, should be chemically identical so that we can track and tag them to where they came from. And that's actually something that we're doing. We just wrote a paper on this where a couple of graduate students and I, these are two of my graduate students, Drea Carrillo and Maddie Lucy, who are doing absolutely phenomenal work. Two of my undergraduate students, Megan Thompson, that are doing absolutely amazing work. We just wrote a paper where we figured out that stars that are born together in these little associations, they're very likely to be chemically identical. And that allows us to be able to track where they came from. In a similar way that we can DNA tag a human being. For example, if I take your DNA, I can tell you X% of your ancestors came from Africa, X% came from Asia, and X% came from Europe. Well, now we can do that with stars. I can say X% of our galaxy came from this other galaxy that the Milky Way ate, and X% came from this other galaxy over here. And so that's something that we're doing now in our group. And it's this is a paper that we wrote just basically trying to do this exact thing. And one of the funny things is that I'm actually a twin myself, and so the press really liked this because it was like twin astronomer studying twin stars to figure out if you can DNA track the stars. And so I just want to quickly end here. I know that at least I'm running out of time, and just say that being in the Indiana Jones, at least in my opinion, of the galaxy is one of the coolest jobs ever. I love the fact that I'm able to go to various places around the world, cost-free to me, and look at the stars and try and figure out where we came from as human beings. Try to find the chemical, learn the chemical composition and DNA of other stars, and try to figure out, hopefully one day, if there's life out there by understanding the chemistry of stars. And I feel incredibly lucky to be able to be an astronomer and do the type of science that I do. Two other things that I hope you got out of this, or I hope that you found interesting, were things like our galaxy, the Milky Way, probably formed both from collapsing gas clouds, but also more importantly, by cannibalizing other galaxies, right? Our galaxy is nothing more than a cannibal. It's eaten a bunch of other galaxies to form itself. And most importantly, you can use the chemistry of stars like the sun and beyond to tag where they came from, kind of like DNA tagging, but for stars. And we can do that now as astronomers. So with that, I just want to say it's been a pleasure talking to you all tonight. I thank the organizers for inviting me. I'm very lucky to be able to do this type of science.
Thank you so much. That was a very interesting talk, and I can definitely see where this can definitely go into future. And I honestly believe you need to get a fedora. You need to have
I thought about it.
You need to get a fedora to fill out the role. So if anybody has any questions, go ahead and leave them down in the comments, and we could be happy to answer them. But while we're waiting, I do have one question for you, sir. For galactic evolution, how does dark matter or dark energy play into this? And will that affect your findings?
Yeah, that's a very good question. So I didn't talk at all about dark energy or dark matter. So dark matter is this dark material that we have no idea what it is. And the way it was found is actually by Vera Rubin, who discovered that if you watch stars move around the galaxy, what you might think, because this is what happens in our solar system, stars that are close to the sun, or stars that are close to the center part of the galaxy move fast. Stars that are further away will move slow. And the idea is that stars that are further away, well, they just don't feel so much of the center part. And so as a result, they just move slower. Well, what she found was actually surprisingly opposite. Stars that are at the edge of the galaxy move just as fast as stars in the central parts. And the only way to do this was to add material to the galaxy in the outskirts, especially called dark matter. And it's dark matter because we don't see it. This isn't expected from the light that we see. This does affect galaxy evolution significantly because the dark matter helps draw in material. So our dark matter halo, so to speak, is quite large. And so it draws in all of the small, what we call subhalos, the smaller halos of dark matter in galaxies into the Milky Way. It does not, however, affect at all the chemical composition of stars. And so the chemistry is a wonderful way to study galactic evolution without having to worry so much about dark matter in any way, shape, or form. However, if you're going to study things like how many things the galaxy ate, or you're going to study the motion of the stars, then dark matter becomes very important. Dark energy primarily exists and affects things on much larger scales, things like the motions between the galaxies themselves. And so dark energy isn't going to play a huge role. Dark energy is, I should say, is like an energy field that is thought to be expanding the universe at a faster rate. That was actually the Nobel Prize of, I think, maybe 5 years ago, the Nobel Prize in Physics. And we don't think dark energy plays a significant role in at least galaxy evolution, as far as we know.
All right, are there any other questions? Let's see if I can pull up the chat here. What insights do you hope to gain from observing with the James Webb Space Telescope, and how large galaxies form?
Yes, that's a very good question. So James Webb is it's not quite up yet. James Webb Space Telescope is the successor of the Hubble Space Telescope, which is in space now. It's a very popular telescope. We're all very excited about James Webb, and what we're hoping. So James Webb is actually in the infrared, whereas Hubble primarily observes in the optical. So our eyes, we see in the optical. We see red to blue. But there is a much broader spectrum of light beyond that. There's X-rays, and which we get, often of our teeth, for example. I just went to the dentist recently. Or there's gamma rays, but those are all higher energy. On the lower energy side, there's microwaves that we use every day for our microwaves. But there's also infrared radiation, which is more like heat rays. And so James Webb Space Telescope will actually mostly peer into the infrared of the electromagnetic spectrum. And one of the wonderful parts about the infrared is that it can peer through dust. And so James Webb is actually going to give us one of the best images and pictures of the central parts of our galaxy and other galaxies that we've ever been able to get, because we just haven't been able to see them because there's so much dust stopping us in the optical. So James Webb will actually be an important resource to be able to understand how galaxies form, especially big galaxies that have lots of dust, because we'll be able to peer behind that dust and be able to see what's behind it. And so we're all very excited about the launch of James Webb. It's not yet launched. It's supposed to launch later this year. We heard that there could be another delay, so we're kind of hoping and waiting, fingers crossed, that it comes up in the next year or year and a half.
Indeed. I know many of us are anxious to see James Webb being launched soon. What books and published works would you recommend studying if you wanted to learn more about your field?
Ooh, that's a good question. So there's in popular astronomy, there's not as many books, recent books, if you will, that have focused so much on the Milky Way. A lot of books have focused on alien life. A lot of books have focused on cosmology. And that actually is a product of the fact that astronomy is very, much like anything, astronomy is very fad-based. And for a long time, the big kind of fashionable things to do were exoplanets, so studying other planets around other stars, and cosmology, studying the universe as a whole. And so galactic astronomy wasn't a super big thing. So there aren't that many books. There's a nice book from Bart Bach, who it's a little bit older. It's probably from the 1990s or so. And Bart wrote a really wonderful book about the Milky Way for popular science. And there's another book there's a series of books that will be coming out. There's a book from Paula Joffre that will be coming out, Paula Joffre from Chile. She hasn't yet finished the book. She was actually one of my PhD advisors, so I know it's coming out. And so she's writing a book actually about galactic astronomy, she's kind of looking at galactic astronomy with a cross-link of female astronomers. So she's going to be compiling not only what has been done in galactic astronomy, but also highlighting a lot of the work that has been going on from women astronomers. And so I'm looking forward to her particular book about the work that we're doing. Astronomy in general, there's a lot of great books. Shonda Prescott Weinstein wrote a wonderful book recently, and there's also a series of wonderful books by Neil deGrasse Tyson and other science popularizers as well. So I'd recommend starting with those particular authors.
Okay. Next question. What are some of the biggest outstanding questions that we still have about our own galaxy forming?
Yeah. The wonderful thing, or not so wonderful thing, but the wonderful thing for me is that there are a lot of outstanding questions. That's why I have a job, actually. And so some of the big questions, right, is we still have no idea how the galaxy formed. We don't know how the galaxy formed. We don't know under what time scales it formed. Did it form a billion years ago? Or we know that it didn't form a billion years ago, but did it form maybe 10 billion years, 11 billion years, 12 billion years? No idea. How many things did it eat to form? Did it eat just one big thing? Did it eat two small things? We don't know. Is our galaxy a typical galaxy? We don't know. So there's a lot of open questions, I think, in the field of galactic astronomy. We actually don't know how it's structured, surprisingly. If you sit down and think about that, right? Our galaxy is the closest galaxy to us. It's the thing that we should know the most about. And yet we still don't know how it's structured. The thick disk component, that fat American pancake component that I was talking about, was only discovered in the 1980s by my PhD advisor, which is part of why I went to go work for him, because I got trained by someone who's discovered one of the components of the galaxy. And so there's a lot even about galactic structure that we still don't know. And so one of the wonderful things that I didn't get a chance to talk about is the telescope that's here in the background in my background is called Gaia. It's a European Space Agency mission, and it's devoted to measuring the first and most comprehensive three-dimensional map of the galaxy. And it's going to do this by mapping the positions for 1 billion stars, and actually accidentally got 2 billion stars. That's only about 1% of the galaxy, but it's the largest data set that we have available. And with Gaia and these other telescopes that we have access to here on the ground, we're now beginning to peer into those particular questions. But those are some of the big questions that are still being asked.
All right, thank you, Dr. Hawkins. That's quite a lot of information. I look forward to hearing what new discoveries you definitely uncover and explore.
Thank you very much.
All right, next up we have Dr. Addie Dove, who is basically going to talk to us about the dusty planetary surface from the ground. She is a planetary scientist and assistant professor at the Department of Physics at the University of Central Florida. She received her PhD in astrophysical and planetary science at the University of Colorado in Boulder. And she focuses basically on surface dust grain and plasma interactions. She also explores these processes through experiments in the labs and has done a ton of different research flights, including parabolic aircraft, and basically got to work with a bunch of CubeSats. So she is well-versed in understanding how our universe works. And if I recall correctly from looking online, she basically is the go-to person in Florida. When people ask questions, she is the one they contact. She basically co-hosts a fun astronomy podcast and Walk About the Galaxy as well. So yes, so Dr. Addie Dove, the floor is yours.
I unmute and start my slideshow. Hopefully you can see that. Great. So thanks again for having me, and it was great to hear all about Dr. Hawkins' talk and his studies of the universe. I'm going to bring it a little bit closer to home now. I like having sort of this broad range of exploring the universe and galaxies, and then talking a little bit about what we can do here on the ground and to study the other planets in our solar system. So I'm going to talk today, as Michelle mentioned, about exploring dusty planetary surfaces and how we can do that in laboratories in various settings. So first of all, I want to show a little video that just sort of highlights a relevant mission that I can use to show some of the different things that we study, that I study in my research. Here we have the landing from the Perseverance rover. So you can see on the right-hand side, there's this video from the descent camera on Perseverance. So Perseverance was landing on Mars. And then we have these two awesome videos of the rest, from other parts of the mission. I like starting with this right now because it's one of the most recent missions we've had, recent planetary missions we've had. It's super amazing that we have these videos of a spacecraft landing on another planetary body. It's awesome to see the excited scientists and engineers who were involved in the mission celebrating there at the end. And it also gives us a chance to talk about some of the different planetary processes that I study and that I'll talk a little bit more about in some other contexts here. So I'm just going to replay it a little bit more really quickly, and I lost my bookmark, but so I'm going to zoom ahead a little bit to showing us some of the descent cameras, so you can see that Mars is a surface that's covered with dust and rock. And as we land on planetary surfaces and as we explore planetary surfaces, we have to interact with them, and we have to interact with these rocky surfaces and these dusty surfaces. And you can see here that as it's landing, it's shooting up all of this dust and rock. And that can be dangerous to the spacecraft. It can be dangerous if you have other things there near the landing site. So if we are developing bases anywhere, or we have other spacecraft landed nearby, all of this can create dangers. And you can see it's billowing up around the spacecraft itself. We lose it in the cameras there. So all of these things are reasons that we need to study these planetary surfaces before we go there with humans and with robots. So I'm going to talk today about all sorts of different planetary surfaces, not just Mars. In fact, most of what I study is not Mars. It's too big, actually, for most of what I do, which I'll explain here in a minute. But a lot of what we do also is with other spacecraft and other missions to places like asteroids. And I wanted to give a mention really quick that today is actually Asteroid Day. So June 30th every year is now Asteroid Day. You can go to asteroidday.org to see some of the celebrations that are going on. I think there's still some live videos with cool interviews and really interesting data that's being shown. And this is every year on June 30th again, is because there's a lot we don't know about asteroids. There's a lot we still need to understand, and there's a lot we want to explore about them, both for future exploration and for what's called planetary protection. So protecting the Earth from potential impacts and things like that. So check out asteroidday.org and potentially events in your area. Maybe not this year because it's probably a little late for that, but think about it for next year as well. So here we have two asteroids, in particular, Bennu and Ryugu, that have recently been the target of some planetary missions, both from NASA on the left, the asteroid Bennu that OSIRIS-REx recently visited, and then Ryugu, which the Japanese Space Agency's Hayabusa 2 mission recently visited. And these are both relatively small asteroids. You can see their diameters listed there, that are of great interest because of what their surfaces look like, where they are in the solar system. And so we sent these missions there to explore them and get really up close and personal. And you can see that these are small asteroids that are different than sort of the spherical objects we a lot of times think about when we think about planets. Asteroids, because they're so small, can have lots of interesting shapes and sizes and are sort of loosely bound together. So the Hayabusa 2 mission that went to Ryugu, we'll start there, landed or did a lot of reconnaissance, had a bunch of different instruments it put down on the surface, and also then did a touchdown on the surface, because both Hayabusa 2 and OSIRIS-REx are returning samples to Earth. So we're actually bringing asteroid pieces back to Earth in forms other than in meteorites and stuff like that. So this is very exciting. The Ryugu samples are actually already back on Earth. This is one of my favorite types of photos that we can get in planetary science. You can see this photo on the right that shows the yellow box is highlighting where we're going to zoom in on the next image. But then you can actually see the shadow of the spacecraft on the asteroid, which I think is so cool. So the sun is behind the spacecraft is taking this image, and it's its own shadow seen there on the asteroid. So it's pretty awesome to be able to visit these planetary bodies. And so then here on the left of the image is that close-in zoom in on that yellow box in the previous picture. And you can see that As we go from further out where things maybe look a little bit rocky, but kind of smooth, as you get closer and closer in and to these really small asteroids, we see that they're actually really complex surfaces and really cobbly and rocky. There's big boulders. You can see the scale bar there for like meter-sized boulders. And there's also lots of really small stuff. The picture on the right is not from underwater, although it kind of looks like it. It's just some camera artifacts, but this is actually from a little sort of small CubeSat, small spacecraft-sized probe that landed on the surface and took some pictures, actually on the surface of Ryugu. So you can see that it's this really jumbly, rocky place. And we think that actually most of the asteroid is just sort of this rubble pile, we call it. So it's just a bunch of these boulders that are sort of loosely sticking together, but there's not a strong enough gravity to really compress it. So it's just this stuff that's very loosely held together. Similarly, the OSIRIS-REx mission went to the asteroid Bennu, that is actually smaller than Ryugu, but it looks very similar on the surface. You can see we have, again, these sort of big boulders, these big rocky areas. You get all sorts of sort of rounded, but also really jagged boulders. And both of these spacecraft, as I mentioned, touched down on the surface. So we can see here, hopefully it will play, that the Hayabusa 2 mission sort of went down close to the surface, shot out a little bit of something, and then collected the sample as it came back up. So you'll see as it descends to the surface here, it's actually moving really, really, really slowly. It gets close to the surface, shoots a little something in, and then comes back up. And you can see as it touches the surface, it makes this giant mess, which you maybe think it's like slamming into it really hard and then moving away, and that's why it makes this giant mess, but it's actually touching pretty lightly. It shoots a little impactor, but if we did this on Earth, it would create barely any mess at all. So just because these asteroids are so small, they're very loosely held together, but they also have really low gravity. And that's what makes a big difference in a lot of this interactions that we see in a lot of our spacecraft interactions on places that aren't on Earth, is that things like asteroids have really, really low gravity because they're so small. Even when we go to the moon has 1/6 the gravity of Earth. So it's going to be much less gravity when we're interacting with these surfaces, and things can sort of make much bigger messes than we're used to. And then next we can see the OSIRIS-REx touch and go. They call it a tag. You can see here, so OSIRIS-REx had the sample canister down on the end, and it sort of goes down into the surface and has some sort of like a little vacuum. I'll replay that one because it's really quick. But you can see here, it's sort of approaching the surface. And as it approaches the surface, this canister goes down in and it actually sunk in more than we expected it to. It swept some stuff up, and then it got all of these particles of lots of different sizes and a sample that it will be returning to Earth. So we can push play, watch it happen again. You can see it does a little correction right there at the end. And again, this is just touching down very gently, so centimeters per second. So it's basically sort of going really, really, really gently and then pushing off. And the pushing off creates a little bit of a force, but the gentle touchdown, and then you still have all of this material flying up. So we really need to understand how and why that happens. So I mentioned earlier that part of the thing that controls all this is the size of these planetary bodies. So for some comparison here, we have Earth, Mars, which has about 1/3 of the gravity of Earth, the Moon, which again has about 1/6, and then Phobos and Deimos are sort of on this picture. They're moons of Mars. Bennu and Ryugu, you can't even see, it's not even a pixel. They're way, way, way smaller. And the size of these bodies is mostly what governs their gravity. And so to do experiments and to understand these surfaces, we need to be able to do things that sort of say, okay, we can ignore gravity or take gravity out of the picture for a little bit. So I'll talk about that here in a second. But first, I wanted to touch on a little bit of something that, some terms, and I actually really liked hearing Dr. Hawkins talk about dust in astronomy, because a lot of astronomers hate dust because it blocks the view of things, but some astronomers study dust because it gives us really interesting information about other parts of the galaxy. And I study dust that's actually just on the surfaces of other planets. So we call the surfaces of these bodies, we say that they're covered in dust or regolith, broken up bits of rock. So regolith is the technical term we use. And it's this material that has built up on these surfaces over time because places like asteroids and the moon don't have atmospheres. So they just are bombarded all the time with little tiny meteorites and bigger meteorites that make craters and break rocks apart. And it just grinds everything down until you have this sort of broken up rocky surfaces. Dust is not the dust that's in your rooms. I'm sure your rooms aren't dusty. Mine certainly isn't. And I definitely never have dust like on my computer monitor. All that stuff is actually a lot of organics due to the fact that we're humans and we live in a place that has lots of organics. So it's very different than the stuff on our surfaces that we have to worry about sometimes. But it is still something that covers other planetary bodies, and we have to worry about it getting on our stuff there. So how do we do this? How do we understand these other planetary surfaces? How do we predict what's going to happen when we go with Hayabusa 2 or OSIRIS-REx to these other bodies? How do we predict what the dust is going to do when Perseus landing on the surface? We do experiments, right? We do experiments and models. So a lot of the experiments I do, and I'm going to go through a couple of different examples of them here, are looking at understanding how small dust and regolith behaves in low gravity and vacuum environments. Because again, there's no atmosphere. So basically all of these surfaces are exposed to the vacuum of space. So how do we get rid of gravity? How do we do experiments in low gravity if we're stuck doing them here on Earth, which for the most part we still are for now? We have a number of different types of ways to do this, and one of them starts in our lab, which is with what we call a drop tower in our lab. So you can see the picture on the right is about 11-foot tall structure that allows us to lift an experiment up to the ceiling and then drop it to the floor. And so in that time, we have about 1 second in which we can do experiments, which doesn't sound like very much time, but if you use a high frame rate camera, you can actually do some really cool science. And the analogy for this is if you've ever been in an elevator and it started falling really quickly, hopefully that's never happened to you, but hopefully you've been on like a Tower of Terror or another amusement park ride where it's one of those that lifts you up really high and then drops you all of a sudden. You sort of come up out of your seat a little bit. Your tummy usually comes up a little bit too. Those kinds of things, you're in free fall for just a little short bit of time. And that's what we're doing here in these experiments. So that free fall is basically like a little short duration microgravity environment. For all of these experiments, they just fall from the ceiling, and so they have to be sort of individually powered. We use batteries, little microcontrollers called Arduinos to control all of our experiments, and we do high-speed data recording to look at the videos. And we do different things like impacts into the surface, so sort of what the Hayabusa 2 mission did to get their sample to come up off the surface. We also do experiments with jets into the material to look at how engines, for instance, like we saw with Percy, how those engines are going to disturb the dust on the surface. Here's a couple of examples of those plumes and jets that we can see on other planetary surfaces. So the Apollo landings kicked up a bunch of dust. You can see that here at the top. We see this picture from Percy on Mars and these images we've seen already from asteroids. And this video is showing a recent Chang'e 5 landing, which is a Chinese spacecraft mission as it was approaching the lunar surface. You can see it landing here. And as it was coming in and landing, my slide just switched. It came down on the surface and created a plume that we can see. So in the interest of time, I'll keep going, but I can come back to that later. So we do some of these plume experiments in our drop tower experiment in our lab here at UCF in the Center for Microgravity Research. In this image, in this slide, you can see on the left, we do these same experiments in 1G. So the experiment is just sitting on the table in the lab. And on the right, you can see when it's in our drop tower in this very brief amount of time. And so here we have some centimeter-sized particles in the vacuum chamber, and we're shooting a jet of air into the vacuum chamber. On the left, I promise it's a video that's playing. If you watch it every once in a while, you can see it refresh and it shoots up some really fine stuff that gets shot up into the air, but all the big stuff basically stays there. And that's because of gravity. But if we do the exact same thing in this microgravity environment, you see particles actually start to float up. And so this is something that helps us understand these differences between doing experiments in 1G on the ground and doing them in a gravity that's closer to something like the moon or asteroids. Here is another example of that with a bigger jet of air. So we put a much bigger jet of air. It lasted a little bit longer. You can see on the left, again, you can kind of see some little stuff fly up, but not too much. But then we make a giant mess in the one on the right. I will say one thing about our experiments is they tend to be messy. We're just like playing with dirt and rocks and vacuum chambers, so it tends to be messy. One way we can get experiments that last a little bit longer is on parabolic airplane flights. So these are Vomit Comet or those zero-G flights, where you can see, you've probably seen images of people like doing Superman and floating on them. And in these, you are in an airplane and you can do an experiment in low gravity conditions. In this case, we're doing one that's looking at rotating a chamber and getting landslides to happen. So in this one, it was just a fun way to show some of our students and myself doing these on flights. So we can do these experiments and it gives us about 30 seconds of data. So an example of that is this next video, which I will loop because it's pretty quick. But you can see here we have a little tray of dirt, sand in this case, in the bottom. And when we shoot a marble into it, this is at 0.05 g, so a big asteroid. And you can see that it creates a little bit, I don't know why my slides are switching like this. It creates a little bit of an ejecta that then comes back down. So you can see there's a little bit of gravity because it's pulling all that material back down. If we do the same experiment at in lower gravity with some different material, it actually just shoots that material up into the air, and because there's not as much gravity to pull it back down, sort of just goes in straight line trajectories out away from the experiment. You can see here that our bed of regolith, our surface that we impacted into, was very different than the sand, so it actually was much harder and compacted, so it had a very different type of ejecta. Okay, so let's, oh, and this is me as an example of running one of those experiments. And then finally, one of the ways that we do even longer duration microgravity experiments is actually a pretty recent offering, and that's through suborbital flights. So for those of you who are in Texas, a lot of these flights have taken place in Texas, both with Blue Origin and with Virgin Galactic. And these flights give us a chance to have about 3 minutes of microgravity, which is so luxurious if you're used to less than a second, for instance. And when you go to a Blue Origin flight, if you have a little bit of time while you're down there, you can actually drive to the McDonald Observatory. So I was able to do that one of the last times I was down there, and it's pretty awesome facility. And so this gives us a chance to do longer microgravity and test technology for surface exploration at a little bit longer timescales. And in these pictures is me and some of my colleagues and some of our students as well. This is an example of a payload that we tuck into a box that's sort of a big office box. There we can put some experiments into and look at these microgravity conditions. We have our flight mascot there, Citronaut Dave. You can see he's the orange dude in the picture there. He got to fly to space, lucky guy. And you can see here in this video that's playing, we can do experiments looking at a couple of different things. This one was looking at exploring some tools and technologies we might use for some future missions. And then also on the left, it was doing a little bit of a different experiment, but it's sort of hard to tell in this image. We also use Dave, this is Citronaut Dave, as our microgravity indicator. So you can see in microgravity, he's nice floating there in the chamber. We did put a nice harness on him. You can see a zip tie harness in blue there. Then as we start to descend and come back after the experiment, he had some gravity on him. He's starting to smush down a little bit. When we had lots of gravity upon rescent, he got a little bit smushed and tired. But then when he was back in 1G, he was perfectly happy. And so he was a good 0G indicator for us to see what was going on in our experiments. And you can follow his exploits on Instagram and Twitter if you so choose. And then this is just the final video I'm going to show as I'm wrapping up. That shows one of my students and myself, and then Citronaut Dave on a parabolic flight. It actually was a flight that was following up the one I showed previously, in which we were doing a bunch of science before this, I promise. This is like one of the last parabolas. Sorry, my hair is in the way there. And you can see Tyler getting his zero-G footing there. And so these experiments and these opportunities are super fun, but they're also really great ways to do science and to understand how we can explore other planetary bodies and use this knowledge to make it safer for planetary exploration and also to do better science as we're exploring those planets. So I will leave up some pictures here and say thank you, and I'm happy to take any questions.
Thank you, Dr. Dove. That was amazing just to see all those different experiments and all those different findings. Are there any questions? Well, as they're starting to roll in, I do have a couple of questions. Is there a particular body that you're interested in exploring in our solar system that hasn't been explored yet? And why?
Ooh, that's a great question. So mostly a lot of my research study is right now is interested in the moon and understanding how we can explore the lunar surface. Partly that's because that's where a lot of NASA's interest is right now. But there are tons of asteroids out there that we think will be interesting to study in terms of having surfaces that are very different than what we've studied so far, having potential for resources that we could harness as we're doing more deep space exploration. So I think a lot of those asteroids are places that there's so many different types of asteroids, and we've only actually been up close and observed a few, and we've sampled even fewer. So being able to sample some different types of asteroids would be really exciting. So for instance, the Psyche mission that's coming up is going to be going to a different type of asteroid than we've ever gone to before. So that'll be super exciting. I'll also say there's a bunch of named asteroids. And I recently was fortunate enough to have an asteroid named after me. So it'd be awesome to explore my own asteroid, but it's a little far away for now.
That is impressive. Nice job getting an asteroid named after you.
Yeah.
My next question would be, has there any in your experiments, when you've done them, have you ever gotten results that you're like, huh, that's weird?
For sure, yes, definitely. So a lot of our experiments involve doing these things in microgravity, which it's cool because like basic physics applies really well. So like if you hit something, it will move off on a straight line trajectory, just like we learn in basic physics. But actually sort of intuitively thinking about some of these things is really hard just because we're so used to how things behave on Earth. So there's a few times where we've seen a result from an experiment, especially on some of these recent parabolic or suborbital flights. And we're just like, why did it do that? And sometimes that's because the experiment probably operated a little bit differently than we expected, because these are all autonomous. And so you sort of have to program how it's going to run. But sometimes it's like, oh, wait, what is this result that we're actually seeing? And that usually leads to really cool follow-up experiments that we have to do. So why did things stick together more than we expected them to? Or why did we get more ejecta from that impact than the other one that we did?
All right, I have a question that came in. Have there been any examples of dust causing failures on spacecraft that have landed on dusty surfaces like the moon and the asteroids?
Yes, there have actually. One, I showed the video of Perseverance at the beginning. That one, there was actually some damage to the previous lander, Curiosity, to some of the masts. And so there was, we think some rocks probably flew up and hit one of the masts that did some of the weather instruments on that one. So Curiosity actually had a little bit of damage from flying rocks. On the lunar surface specifically, most of our landed vehicles have landed very, very far away from other from other vehicles or other surface features, right? So we've mostly landed things far apart from each other because we've only been there a few times and because we wanted to explore different regions. The only time we landed kind of close to another spacecraft was one of the Apollo missions that landed near one of the old Surveyor missions. So Surveyor were a series of completely robotic missions that explored the lunar surface before we sent astronauts. And on that mission, we landed, it was still several kilometers away from the Surveyor lander, but there is evidence of scouring of the surface from rocks and really fine particles that went that full distance and scoured the surface and sort of sandblasted parts of the surface of the lander. And we've seen that from some coupons that the astronauts cut out and brought back. Another thing is just when, in addition to landing, when you're then exploring on the surface, astronauts are going to kick up dust. If you have rover wheels, they spin and they kick up dust differently. There were lots of issues with the lunar rovers kicking up dust, and it's sort of behaving a lot differently than we expected. So all of these different, both mechanical and plume or engine interactions, can cause it to be really messy. And so we need to either be able to isolate that stuff or just understand how far away to put landers, or if we need a landing pad or something like that.
Next question. What drew you to planetary surfaces?
Ooh, so I've been interested in astronomy for a long time, since I was little, but I've always also been interested in space exploration. So I think that doing this research that I do and research that other folks do really looks at that intersection between science and exploration, because we're sending robots to these surfaces and we're sending humans hopefully soon again to some of these surfaces, and maybe me, for instance, right? I could go do my research on the moon. So it's that aspect of mixing both the physical exploration on the surface of the body and doing really interesting science to understand how these planets came to be and how they evolved and how we can understand them better, that drew me to this specific part of planetary science.
Awesome. What books would you recommend studying if you wanted to learn more about your specific field?
Oh, I should have been prepared for that question. So there are a lot of great books. I don't have any off the very tip top of my head, but there are a lot of really great books about sort of robotic exploration in general, and there have been some pretty cool ones about like Mars exploration and the Mars rovers more recently, because there's been a bunch of those, right? And we've been able to do some comprehensive studies of those. So those really give you a good idea of what some of the challenges of exploration are. I'll have to think a little bit more about there aren't too many books that are like dust. So maybe I'll need to work on writing that one or something.
Hey, if you could write it, that would be an awesome title. It's a book about
I know, right?
dust.
Dust. But yeah, so I mean, there are a few other books that talk a lot about like planetary surfaces, about exploring asteroids. If you're into science fiction, there's a lot of interest in using asteroids to both in actual life and using asteroids as resources and to explore asteroids. But there's also some cool science fiction work that's been out recently. Shows like The Expanse really look at exploring those surfaces and what it means in terms of resources and also human exploration, and like how you can do some of that stuff. So that's been of interest for a long time. And I think a lot of those sort of a little bit more fiction works, but highlight a lot of the good science that's important. Books like The Martian, right, actually look a little bit at exploring planetary surfaces and do a decent job at doing some of the real science and engineering there too.
Are there any other questions?
This is a gingerbread.
You'll have to excuse
questions from our very young audience.
Yep, I have my little one joining us today. She loves the planets and astronomy.
Awesome.
As they say, start them young.
Exactly. It's never too early.
Are there any other questions, folks? Well, if there are no further questions, Dr. Hawkins and Dr. Dove, thank you so much for your wonderful talks. I know I've learned a lot from them. And for those of you that have your favorite beverage, cheers to the universe and have a wonderful night, folks. Be sure to check us out on Facebook and our YouTube channel. Have a happy 4th of July weekend. And hopefully come August, Astronomy on Tap will be back in the Blue Star Brewery. So keep posted for when we get back. Until then, have a wonderful night, folks.